Bismillah ar-Rahman ar-Rahim. Actually, these are our last two lectures in assembly technology, in which I'm going to talk about design for automatic assembly. First, I'm going to talk about design for automatic assembly on automatic machines. Then, after that, I'm going to talk about flexible assembly systems. In automatic assembly, I'm going to use the book design for assembly written by Bothroyd and Duhurst, and this book you can get a soft copy of it from the library. I gave the students the book before, but if you lost it or if you want a copy, you can go back to the library and get a soft copy of it. Let us start our lecture. Actually, Boothroyd started by classification of parts for automatic assembly and classifies them as disk. Actually, it classifies them as rotational and non-rotational. So rotational parts, disk, short cylinder, long cylinder, and non-rotational parts, flat, long, and cubic. And those actually the dimension of them. I can't go through the dimensions in this short lecture, but you can go back to the book and read them, or you can go back to this lecture and look at them, right? And even there is a hard copy, a soft copy of this lecture as PDF. You can go and stop on it page by page, okay? And then he divided the rotational parts as so. A part whose basic shape is cylinder or regular prism, whose cross-section is regular polygon of 5 more sides, is called rotational part. If it is got 4 sizes, it will not be rotational part and will be non-rotational part. But if it's more 5 or more, it will be rotational part. In addition, triangular or square parts that repeat their orientation when rotated about their principal axis through angles of 100 degrees or 90 degrees respectively are also rotational parts. L is the length, D is the diameter of the smallest cylinder that can completely enclose the part. Is the length of the longest side, C is the length of the shortest side, B is the length of the intermediate side of the smallest rectangular prism that can completely enclose the part. Actually, he said A is the length of the longest side, C is the length of the shortest side, and B is the length of the intermediate side. This is why he used those L, D, A, C, and B, because in his book you find a small drawing which show you the different dimensions, and those dimensions, as I said in the previous lecture, the dimensions of the part will has something to do with the efficiency of feeding, and definitely some parts which they have got different orientations, and in this book actually he tried to estimate the time for feeding through feeders. Rotation bars. A rotation bar is alpha symmetry if it does not require orientating end-to-end. This bar can only be inserted into the assembly in one direction, then it is referred as not alpha symmetry. A beta symmetry bar has rotational symmetry and therefore does not require orientation about the principal axis. That means the two sides are the same. A beta symmetric step chamfer or groove is a concentric reduction of the increase of the in dimension. Its cross-section can be circular or any regular polygon. These significant features should be ignored. Parts in this category have an alpha symmetry external shape, but the internal surface composed perhaps of cavities, counterpores, grooves, etc. require that the part be oriented end to end. Actually, difficult to just in this voice lecture to explain rotation and non-rotation paths. This is the first thing. The second thing, also to understand the standards which set by both Freud and Hurst, it required very long time of study. And if you are not going to work in this area specifically, or your project is in that area, just try to understand it generally. Actually, these tables and this table for handling of rotational parts. I can't explain the table in this lecture, but just have a look at it in some details. As you see, the table got two digits, digit on the top and digit on the side, and those two digits will show the difficulty on the part feeding. As you see, part is alpha symmetry and beta symmetry is got digit 0, 0, and the efficiency is 0.7%. And if the part not beta symmetry, you find the second digit got maybe got beta asymmetry projection steps and so on, or shuffle or something like that. Then after that he tried to divide it on side surface, on the end surface and so on. Actually, if you want to understand this table, you need some time, and at the end of the table you find a table which is blocks which are empty, where you can't handle the part automatically. This is what Professor thought. Let us look at the rest of the table, and you see all the blocks which are empty are for manual handling. As I said, it's difficult to understand the table just unless you take your time studying it in details. A non-rotational part, again, a a rotational symmetry of 80 degrees about the axis. That means it is 180 degrees about the axis, means that the same orientation of the part will be repeated only once by rotating the part through 180 degrees. Step chamfer or through groove. Those features actually you can find, like step chamfer or through groove, are features that can be seen in the silhouette. Exposed feature, that means recesses and something above. I'm not going to go on that, because as I said, if you want to understand this, you need a lot of time to understand it, and just I want you to know how they did the design, not how to do the design. And then rotation paths, again, this same slide, and here is the automatic handling of non-rotational path, and we find it as the same. And this is the rest of the table. Then Actually, this is for handling, but there are additional costs which he gave to his component on his table. He said that if there is difficulties on the part feeding and orientation, this will cost more money. And here he tried to calculate the extra cost, and he said that parts can be sticky, delicate, uh, tangled, and so on. And he put some cost for those parts. And here parts can be also very small to handle by the machine, abrasive, and so on. Actually, those main features are flexible, delicate, sticky, light, and those will make it difficult for the machine to handle or for the feeder to feed. Overlapping large parts which cannot be fed through small feeders like hoppers, vibrated feeders, and so on also uh, has got additional cost. And very small parts as well, because the machine, if the part is less than 3 millimeters, cannot handle. And part are nesting, which tangles together and nest together like straws in the nest, also difficult to handle. Our civil nest in this case, definitely he is going to go to manual assembly. Tangle parts, severely tangle, abrasive, and so on. You can go through that later. Then, after we talked about the handling, we want to talk about the insertion. The handling is by the feeders, and we talked about the feeders in previous lectures, and the insertion is by the head. And this is a table which shows also 2 digits for insertion. Now we have got 2 digits for handling, 1 digit for difficulties, and again 2 digits for insertion. And here is the table. You see here the table, the insertion, easy to insertion or not easy to insertion. You can go through the table and you find a number which will be moved again later. This is the middle of the table, and this is the end, the last part of the table. If we look at the table again, here is the table complete. It's not mentioned in the book, of course, but I divided it into 3 divisions so as you can concentrate on each division, right? Here, actually, a simple example. This is a typical example. Actually, you find this example in Postgraduate books, all of them, and you find it in other assembly books, which is a kind of diaphragm, which made of those parts, 2 bolts, bearing housing, a plate or diaphragm, or the diaphragm or a spring, 2 washers, and 2 nuts. And he wants to assemble them, to redesign the product so as to assemble them in an automatic machine. First, of course, he is going to analysis the part for assembly, and he is going to use a table. You can find these tables in the book, and as you see, he tried to find, first of all, he started the part from the bottom to the top, and he started from 2, and 2 are the screw. You find the screws on the top of the drawing. If you go back to the drawing, you find it, he starts from the top to the bottom. Screw, bearing housing, plate, washer, nut, and diaphragm as full assembly. Actually, number 1 is diaphragm full assembly, and it didn't been written down here. and then after that he tried to put the 5 digits on column 3. He tried to put the numbers which he got on other columns, and then he tried to find out whether the path can be eliminated or not, and that is column 14, and we are going to talk about this later. And you see here, this is a full table. Actually, that one I put so as you can look at. And he tried to find in column 14. He tried to find the theoretical number of parts of the assembly, and because this will give the efficiency, and you see the efficiency is 3.4%, which is 0.03 he calculated, as he calculated. The plate cannot be assembled. If you look at this, he said the plate should be assembled manually. If you look at this slide, find it, the plate number 4, part number 4, cannot be assembled with the machine, so should be assembled manually, and this actually is a problem on the design. And if you go again, you find the efficiency is very low, 3.4%, which is very low. And the blade will, it's another cost. Now he changed the design to this design, where part 2 is a plate just with one hole, and the bearing housing with a recess, and then the assembly will be very simple like this. If you look at the table, you'll find it two parts, and again he's going to go to the tables and find out all the numbers or figures, and then he calculates the efficiency, and the efficiency now is 32%. Actually, the efficiency here, it's just a number. It is not a real efficiency, but here you see the efficiency increased by 10 times, and that means the cost is going to be less on assembly. And now this is a table. Actually, you can go on it later. The diaphragm the diaphragm assembly the redesign, and let us look at the bottom of the table, and you find the efficiency is 0.32. Boothroyd on his table also calculates the cost, but for us the cost is varies from place to another, so we didn't concentrate it on the cost, right? Another way of redesign, because this plate with two holes, very difficult to assemble to be oriented to the machine. But now, if you look at design on figure 15, where it has got two edges up, that means it can be easily fit, and you can with these features find out the position of it. The other one is to have two cuts, identical cuts on the sides, and this also will make it easy to fit. through a feeder. Another example is also an example, well-known example. In the left is the original design, in the right is the modified design. You can go through it, but simply if you look at that one on the left, it got about 7 parts, and if you go to the one on the right, you got only 5 parts. And also the screw will take very long time on assembly, as well as on the left one there is holes which make it difficult to reorientate the part through feeders. And the second one on the right hand got no holes, and the cover just to be pressed down. This will reduce time of assembly for the assembly machine. Let us look at the example in details. And here is the example. If you look at the real design, here actually those tables are modified from postload table, and you can use them, and you might find them easy. Again, the feeding code is the same code, and you can find it, and the orientation efficiency you can find from the table. And at the end of the day, he put a cost for hour, and the cost here, as you see, total cost is $16.94, and minimum number of parts is 3. Where in the other one, but you have on 0, 0, that means those parts can be eliminated. On the other one, only one part can be eliminated, and the other parts are real or parts which we cannot eliminate. But you find here the cost of assembly is $2.81, and that is drastic reduction in cost. Right. Now let us talk on robotic assembly. I think you have studied robotics somewhere else, so I'm not going to talk about robots, but I want to talk about robotic assembly and flexible assembly systems. Here, actually, this is the first design station being made by Stanford University for a robotic assembly machine. You find on the left what's so-called a belt feeder, and on the right linear feeder and pole feeder. And on the table there is a pallet with parts which difficult to feed. Then there is a fixture, and the robot will go through all the feeders taking parts and assemble the product. Actually, this station is a research station, and it is the first ever station being made for flexible assembly systems. This is another example. Here actually there is a computer added to the station. In the first one only you need you need to only to try to put programs or program the robot. Here the computer can send the program to the robot directly. And here is another station with 2 robots. You see the same feeders, but this has got a transfer line where the products move from place to place. And here another one with a transfer line, similar to the one we have seen just now. But if you look at this, at the end of it, there is a manual assembly station. And here is the first ever machine made on flexible assembly system. It's not very clear, but here you can just change the feeders and the programs, and the robot will do different types of assembly, because as we know that all automatic assembly machines are dedicated machines which do only one job and forever. And if you want to do another job on the machine, it will never be done unless you modify or change the machine. Right? I think this last two lectures on this subject. Thank you very much for your attention. Please go find the books which show more details. In automatic assembly, actually in design, I'm not going to, I don't want you to go deep in design, just to have the idea of types of machines and so on. And I hope you enjoy your subject, and please try to answer the questions for the tutorials and submit them to the secretary. Thank you very much. والحمد لله رب العالمين.